Hi everyone, this is Dr. K. Anita, Associate Professor EIE Department. I am here again with Electronic Devices and Circuits. Today's topic is Introduction to Bipolar Junction Transistor. Bipolar Junction Transistor working principle and the other configurations will be discussed over here. So a bipolar junction transistor is a current controlled semiconductor device which is used in order to perform the amplification and switching. It has basically three terminals: emitter, base, collector. So there are basically two types of BJTs, NPN and PNP, formed by sandwiching P type of semiconductor in between two N type of semiconductors. We will get NPN transistor. Similarly, two P type of semiconductors sandwiched between N type of semiconductor sandwiched between two P type of semiconductors will be giving PNP transistor. So basically for the transistor to work, it has to be biased. So biasing is nothing but application of external energy, external power supply. For example, the first figure shows us NPN transistor. So this arrow indicates the type of the transistor. Arrow tells the direction of the conventional current and the type of the transistor. So this arrow not pointing in, we can remember not pointing in. So in such a way we can remember the arrow. So now NPN transistor, and over here it is shown emitter terminal, base terminal and collector terminal. So the connection, basically the BJT works in three regions of operation. The three regions of operation are active region, saturation region and cutoff region. So the basically cutoff region. The type of the biasing decides which particular region of operation the BJT will perform. So, for example, for the transistor to work in active region, the input junction, which is emitter base junction, should be forward biased and the collector base junction should be reverse biased. Whereas for the transistor to work in the saturation region, both EB junction and CB junction should be forward biased. And lastly, for the transistor to work in cutoff region, the emitter base junction and the collector base junction should be reverse biased. Over here we are showing the transistor in active region. We can observe over here emitter base junction. This is N. This is N, this is P and this is N, NPN transistor. So in order to forward bias the NPN region, we have to connect the negative terminal of the battery to the N terminal of the NPN transistor. So that is what is done over here. So here we have the battery, the negative terminal of the battery is connected to the N type of the BJT. So for example, so over here we can observe that the terminal over here, the negative terminal of the battery is connected to the N of the NPN transistor, and which is going to forward bias the transistor in the EB junction. Similarly, we can observe that the positive terminal of the external supply has been connected to the N terminal of the BJT, which is collector, leading to the reverse bias condition. So we have satisfied the biasing for the active region. EB junction is forward biased and CB junction is reverse biased. So the first figure is showing the symbol of the BJT. The symbol of the BJT is biased. Over here, the second figure over here is showing the schematic of the BJT, wherein you can see N, P, N regions are shown here. So negative terminal is connected to N and positive terminal is connected to N, leading to the active region biasing. So here the current conduction is shown, the direction of the current is shown here. So IE is following the direction of the emitter terminal. So this IE is the emitter current. The current flow of the emitter is shown with the help of this arrow. So this is the base current IB and this is the collector current IC. We know that IE is equal to IB plus IC, hence fulfilling the equation IE is equal to IB plus IC, the arrows are shown. Similarly, we can also tell that junction J1 and junction J2 are the junctions between the emitter base and the collector base respectively, telling that inferring that the junction J1 is forward biased, junction J2 is reverse biased. Hence, I can conclude that the NPN transistor over here is biased under active region. So NPN transistor is biased with respect to the circuit diagram, that is common emitter I am showing here. So this is the circuit diagram showing that the base emitter junction is forward biased and the collector emitter junction is reverse biased. We are in the active region. Coming to the symbol of the BJT, in all the circuits diagram when we draw, we will use the electronic symbol. So this is the electronic symbol of the BJT. So here we have the emitter terminal showing the arrow, base and collector, and emitter terminal, arrow, base and the collector, and this is in the form of IC. Nowadays we are obtaining it. So the structure of the construction of the BJT, we have emitter, base and collector, three regions in the BJT, bipolar junction transistor. Coming to the level of the doping, we can discuss the emitter is very heavily doped because this is the one which is going to inject electrons for conduction. Base is very thin and very lightly doped, hence it has very few number of charge carriers for conduction. Coming to the collector region, we have moderately doped, so it has between emitter and the base the electrons or the holes or the charge carriers we can observe. So this is the structure of the BJT. Coming to the working of the BJT, so active region is the one, active mode is the one in which maximum number of applications we can find. So over here we have already learned that the base emitter junction should be forward biased, leading to 0.7 volts for silicon, 0.3 volts for germanium. The second junction, which is the collector base junction, is reverse biased. A small base current IB flows leading to IB, which will be in microamps or nanoamps. Large number of electrons move from emitter to base and then base to the collector. Very small amount of current we can observe, that is IB as I said. So this is going to control large current in the BJT. So coming to the current relation in the BJT, we have three terminals, emitter, base and collector. Emitter current IE, this is the emitter current IE. I can write it as emitter current I suffix E. Emitter current is equal to the base current and the collector current. So this is very, very important. Following the direction of the current flow arrow given in the emitter, we have, this is also depicted by that. So emitter current is equal to the base current and the collector current. But to be very specific, emitter current is in the milliamps, collector current is in the milliamps, whereas the base current will be in microamps or nanoamps, which is very, very small as compared to the milliamps IE and IC. Hence we can conclude, we can say that approximately IE is equal to IC. Approximately emitter current is equal to IC. So this is what we finally have. So here in the figure shows the PNP transistor. We have discussed till now NPN transistor. Over here this figure which is showing PNP transistor, the base emitter junction is forward bias because it is a P type of semiconductor. Hence the P terminal of the battery is connected to P, leading to forward bias at the input side or emitter base junction. At the output side, we observe that the P region is connected to N negative of the battery, leading to reverse bias. Hence, we are in the active region of operation, active region. So, P and P biased in the active region, the P emitter and the base is forward biased and the collector and the base is reverse biased. Over here, with the help of the electronic symbol, same thing is depicted. So this shows the current flow in the PNP transistor and current flow in the NPN transistor. Emitter current is flowing, coming to emitter current, and base current is equal to, so emitter current is equal to base current plus collector current. Just now we have learned. Similarly in the NPN, so emitter current, which is nothing but base current plus collector current. So this is what we have learned. So as I said, we have basically three operating regions for BJT: cutoff region, active region and saturation region. In the cutoff region, there is no base current. Transistor, we can assume it as off condition. It acts like an open switch. In the active region, we will forward bias the EB junction and reverse bias the CB junction as discussed. It is used for amplification. Most of the applications we find in the active region. So over here we can say that the collector current is equal to base current into the beta. What is beta? Beta is the current gain. So beta, what we have is the current gain. And the saturation region, lastly we have the saturation region, this is third one, which is fully on, acts like a closed switch. So all the applications, for example oscillators, amplifiers, clippers, clampers, comparators, all the applications we find in the active region, whereas all the digital applications like switch, so we find under the cutoff region and the active region. So these are the regions of operations for the BJT. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.